Okay, so today I'm going to work this final from fall 2020. My name is Wayne. My student ID number is whatever. Okay, so anyway, if you go work this one, if you look at it, it's got it's got you kind of randomizing the numbers that you're using these problems. I've just gone ahead and entered them in over here. So P in this problem, for example, is 5 kilonewtons. Okay, so draw for the beam and loading shown, draw the shear and bending moment diagrams and determine the magnitude and location of the maximum shear and bending moment. Okay, so I'm going to go ahead and draw these things, although I think I'm getting a little ahead of myself. I am getting a little ahead of myself because we really need to make sure that we get the reactions at B, right? And so I'm going to do that. So let's see, how do we do that? Okay, so it's, usually on these, people kind of ignore the free body diagrams. They do it on the figure itself. I'm going to go ahead and draw a little quick free body diagram just because it's going to make my life easier, right? Okay, so let's see here. I've got 2 kilonewtons per meter downwards for 1.2 meters. So 2 kilonewtons per meter for 1.2 meters. If I multiply those two, so if I multiply this 2 by that 1.2, I get 2.4 kilonewtons. Okay, and it's acting 0.6 away from this edge, right? And then 0.6 until it gets to this 5 kilonewtons going up, which I'll probably just draw on the top of this thing. I don't know why, but why not? Okay, and then there's another 0.6 meters. Oh, these numbers are all very clean, right? Okay, and then I get 3 kilonewtons per meter for 1 meter, right? So that means at the centroid of this rectangle, 0.5 and 0.5, I've got 3 kilonewtons per meter times 1 meter, which is 3 kilonewtons up. 3 kilonewtons. Okay, now on this far end, now that I've drawn everything that's on that drawing, I'm going to zoom in right here. And on that far end, I've got a wall. So I'm going to erase that wall. And I'm going to replace it. Excuse my puppies. They'd like to bark. I've got, this is B in the X. I've got B in the Y, which I don't really know. I could probably look at it real quick and figure out which way it's going to go. But I'm going to go ahead and make it vertical. And then a positive moment. Okay, so we're going to call this moment at B. All right, so now we'll go ahead and that's all we need now. So we don't need to worry about the rest of the universe. Okay, the nice thing about cantilevers usually is every equation will solve itself because you just have one unknown in each equation. So sum of the forces in the X equals 0. Bx is my only force in the X, so it equals 0. Doom, done. Okay, sum of the forces into Y equals 0. So I've got negative 2.4 kilonewtons. Kilonewtons. These kilonewtons? Oh, yeah, they are kilonewtons, okay. Plus 5 kilonewtons, plus 3 kilonewtons, plus By equals 0. So By is, what is that, 8 minus 2.4? What's 8 minus 2.4? 5.6 kilonewtons? Okay, and then the sum of the moments at B equals 0. Okay, and so now I've got this 2.4 kilonewtons. Okay, and let's see here. What's that total distance? Is a half plus a half, that's 1, 1.6, 2.2. Okay, and that's going that way. So that's a positive moment. Okay, and then I've got that 5 kilonewtons. There's its moment arm, which is what, a half plus 1.1, so it's 1.6 kilometers. Okay, and it's going this way, so it's a negative. And then I've got a 3 kilonewtons. Of its distance, which is a half a meter. Okay, and that's going negative. And then By and Bx go through B, so they don't count. And then MB is, I drew it positive because that's the way I like to do it. Okay, so if we solve this equation, we get MB equals 4.22 kilonewtons times meters. Okay. Now you have to be very careful with these, because if you screw these up, it's gonna really mess you up for the problem. So it's just something you really got to make sure that you get these correct, because they're gonna affect everything. Okay, and it's something you should be aware of when you do your shear moment diagrams. If you get to the end and they don't, to the either end, in this case A or B, and you come back to the end and you have at the ends and you don't have a moments coming back to 0 or shears coming back to 0, then you made a mistake. And usually the mistake is right in here. In fact, just now when I plugged this into the calculator, I got 5.78 kilonewtons times meters, which of course would be a massive error, right? Not something that, or not a massive error, but it would have been a small error, but it would have created problems. And, if I had just remained consistent with that, then, depending on the grading, if I'm doing the grading, it's probably okay, but different people grade different ways. So if you're not my student, just be aware of that. So usually if there's a problem and it doesn't come back to 0 at the ends, usually it's because of something like this, like you plug it in your calculator and you got the wrong number. Okay, so if that happens and you have time, the first thing you need to do is you need to come back here and check these equations. Okay, so anyway, so we're going to go back over here, and since all my other forces are in red, I'm going to go ahead and do some red forces over here. And let's see here. So, or not forces, I guess, forces and moments. Okay, Bx, I'm not going to bother writing on there because it's a 0. By is 5.6. By is a negative 5.6, right? Hopefully you guys caught that. That was an error, for example. So the By, so we're going to put it right here. 5.6 kilonewtons. That's important that we get the right sign on that. And then this moment, let's go ahead and check the moment on that. I mean the sign on that. It looks okay. So it is a positive 4.22 kilonewtons per meter. So it's going to look like this. 4.22 kilonewtons times meters. Okay. So now we're going to scroll down, and unfortunately this one's a little bit narrow, so it's kind of hard to see. Anyway, so let's go ahead and do this. Let's see what we can do. Let's draw a little line right here, like that, and we'll go ahead and get our shear diagram. And we're going to do this in kilonewtons, and we're just going to do what it tells us to do, right? So we're going to start here, and it tells us to go down by 2 kilonewtons for every meter, okay? Grand total, we're going to go down 2.4 over that total distance. So I'm going to start at 0 and I'm going to end at negative 2.4. So let's call that like right there. Okay, so this is negative 2.4. I don't need units because I already wrote them right there. Okay, this is a steady down 2 for every meter, so it's going to look like this. Like that. Okay, so now we're here and we're going to attack the next force, which is this 5 kilonewton force right here. So we're going to go up 5. So we're at negative 2.4. So we're going to go up to 2.6. So let's see here. That's about right here. If I'm using each square as a half. I really hate the fact that I've decided to use black. It's always better to use a different color than the color you're drawing on, right? Anyway, so, and then nothing happens in here. So we're going to let me label that 2.6. So if nothing happens in there, then nothing will happen to my shear, and we will just stay there. Okay. It's gonna get ugly, isn't it? Well, it's gonna go up another 3. So I'm gonna pause this. I'm gonna redraw this with a different scale. All right. So I just redrew it in blue because I prefer blue. It just stands out on a black graph. Also, blue is the best color. Let's just be honest. But anyway, so I recognized that I was crowding my other area, so I needed to rescale it. Anyway, so we're going to go. Now we need to go up 3 kilonewtons per meter over 1 meter, or as we look over here, a grand total of 3 kilonewtons up. So I was at 2.6, so I'm going to end up at 5.6. So 1, 2, 3, 4, 5.6 is about right there. Okay, and notice that this is a steady, like we're going up the same amount for every meter. So that means we're just going to kind of go up like that. Okay, at which point we're going to go down 5.6. And there we are. Okay. Let's see. Oh, wait, sorry. This was 5.6. This is still 2.6, etc., etc. Okay. So now what we need to do is we need to find these areas. And maybe I'm going to label them in red or, I don't know, just some other color. Right? So the area of this triangle is 2.4. The first triangle is 2.4 times a base of 1.2. And then we're going to divide that by 2, right? So it's basically 1.2 squared. So that's 1.44. And it's a negative 1.44. And then we've got a rectangle, which has a width of 2.6 and a height of 2.6. So 2.6 times 0.6, and we get 1.56 plus 1.56. And then we got a trapezoid. And some of you guys will split this up into a rectangle and a triangle. I don't do my trapezoids that way. What I do is I do the average of 5.6 and 2.6. Okay, so the average height of this thing is 2. And the total width of it is 1 meter. Okay, so this was how I would get the area of a trapezoid. It's a lot quicker than doing base times height of a triangle and then adding, base times height of a rectangle. Anyway, so we're going to get 2.6 plus 5.6 divided by 2. So we get a 4.1. So this is a positive 4.1. All right, so now we're ready. It is customary, and again, I always say this is customary. I don't know why, but it's customary to shade these in. I have no idea why, but they always do it, okay? But anyway, so the only numbers we need now for the next graph are these numbers right here and this number of this moment, because we're going to do moments now, right? And unfortunately, we have to zoom out, which is not, ideal. I like to keep things, in the right... I don't know what the word is. Okay, so anyway, so here we go. So here's a moment, and it's kilonewtons times meters. Okay, and again, I'm gonna switch back to blue, and we'll go ahead and draw it. So I'm gonna start right here at 0, and then I'm gonna use this 1.44. So I'm gonna end up at negative 1.44. So let's put that dot about right there, negative 1.44. Okay, I'm not gonna worry about the shape of that just yet. Okay, now I'm going to go up 1.56. So that's going to put me at 0.12, which is a really annoyingly small spot, right? 0.12, right? And again, I'm not going to worry about the shape between those lines just yet. And then I'm going to go up to 4.1. So that's going to put me up to 4.22. So if I take the 0.12 and I add the 4.1, I'm going to end up at 4.22. So 1, 2, 3, 4.22. Maybe that's like right there. So now I'm at 4.22. And that's when I come across this thing. And I'm going to go... Now, remember the sign convention here is the opposite of what you want it to be, right? So this is a positive moment. So we're actually going to graph it as a negative, which is totally annoying. But it's going to go... Basically, we're going to go down by 4.22 because of that thing. Okay? Now we have to figure out how to connect these dots, okay? And let's go here. And what I want you to remember here is that the value here is the slope here, okay? So the slope so the value right there is 0. So the slope right here is 0, so it's going to be flat, right? And the value right here is negative, but very small. So we're going to have a negative slope, but it's going to be small, right? And the value here, so the values here are negative and getting more negative, right? Because we're, so that means our slopes down here are negative and getting more negative, right? So in other words, the slopes are going to be concave downwards, okay? And that, if I'm grading, that is how I would grade these. I'm looking for that negative concavity, right? Okay, so to the best of my ability, that is a concave line. Okay, over here, notice the values are positive and constant, okay? So the slopes over here are positive and constant, Okay, and constant really is the key here. We know it's positive because to go from negative 1.44 to positive 1.12, you have to go upwards. But the fact that it's constant, the slope is constant, means we just got this like straight line. Okay. Now over here, the values are, the values are positive, and they're increasing. Okay, so the slopes down here are positive and increasing. Okay, so we're going to go, so in other words, it's going to be concave upwards, right? So here's a positive slope. Here's a more positive slope, right? So it's going to curve upwards like that. Okay, to the best of my ability, that's how I would draw it. Okay? And that's the whole thing. Okay, so there you go. And that's all it is. So yeah, so that's the whole thing. And then what we would want is we want to know where's the maximum shear and where's the maximum moment. Okay, so let's see here. The maximum shear is right here. And the maximum moment, oh, look at there, both all the way at the end there. Okay, so we would go down here and we'd say, okay, well, the maximum shear is 5.6 kilonewtons. Don't forget those units. And the maximum moment is 4.22 kilonewtons times meters. It's all crammed in there. And it is located how far from A? Well, A is all the way on the left, so the total distance of this thing is 1.2 times 0.6 plus 1. Is that 2.8 meters? 2.8 meters, 2.8 meters. Boom, done. Okay, I'm not going to get into the grading of this because this exam happened several semesters ago. Okay, determine the centroid of the shaded region. Okay, I could, of course, or I say I could, anybody could. We could do this with horizontal or vertical boxes. We're going to avoid, oh, by the way, K is 3 in this case. We're going to avoid this horizontal box. It's actually wouldn't be that difficult, but the real problem for it is there's like a void space right here between it and the axis. You know, if we see this space right here. So it's usually easier if you don't have that void space. Especially if that void space is changing. Like notice that void down here is different than it is over here, okay? Now everywhere where that void exists, it is defined as x, right? Because this location, every location on here is x comma y, right? So it's changing in a simple way in that it's always x, but we don't want to deal with that void if we can avoid it, okay? Avoid, okay, anyway. So it is easier to not do that void. So I'm not going to do that right here. Okay. What I am going to do is I'm going to do a vertical box. Okay, and the vertical box looks like this. Okay, and usually it's customary to kind of, okay, if we do it like that. Okay. So there we go. And we're going to zoom in here because there's no reason to have the rest of the world be part of this. Okay, so this location right here on the line, like every location on the line, is x comma y. Okay, that is a very ugly y. X comma y. And what we're going to do here is let's go ahead and define what that means. Well, what that means is that means that the distance here is x and the distance here is y. Okay, which is cool, which is very helpful for us, right? So if I wanted to define this little, this shape somehow, right? I can say that it's got this shape has a height, this rectangle that I've drawn has a height, I guess we would do it like this, a height of y. Okay, it's got a width, okay, this is a little dx, right? Differential dx, okay? So it also means that means it's got an area of y dx, right? It's actually a differential area. So it's a differential area of the whole thing, but if I just want to know the area of this little rectangle, that's what it is. Okay, now because we've done this before, we know we're also going to need to know this location right here, that's the centroid, right? So that's x, oh man, that is hard to see. Let's go with, let's go to black, okay, x tilde, y tilde. Okay, and that's the location of this dot, the centroid, right? And so the centroid has coordinates. Okay, and we need to figure out these coordinates. I'll note that in the x direction, it's got the exact same coordinate as above it, right? Okay, in the y direction, however, okay, it's a rectangle, so this right here is going to be half of that. Right? So if this is y, then this is y over 2, and this is y over 2, and the coordinate of this thing is y over 2. All right, so now we should be ready. Okay, now we can plug and chug this this sucker. And it looks like based on how I'm doing it, I'm going to be way off here over to the right. Okay, so the equation for this sucker is, let's see here, is x bar equals the integral of x tilde dA over the integral of dA, right? And for y bar, it's integral of y tilde dA over the integral of dA. Because the integral of dA is on the bottom of both of these, I'm just going to go ahead and do it on the side so I don't have to do it twice. So let's see here. So the area equals the integral of the dA, right? So the area equals, now the dA is just that, right? It's the area of that little, it's the differential area, right? So integral of y dx, okay? And if I want to know, where I'm beginning and ending, well, I'm going from x equals 0 to x equals 1, so from 1 to 0. Okay, and the only thing that's stopping me right now from, just solving this is the fact that this is an x and this is a y, and I don't want to do that, right? Or I can't do that, right? So I need to replace y with kx to the fourth. Of course, k in this case is 3, so 3x to the fourth. Okay, so we're going to go a equals integral from 1 to 0 of 3x to the fourth dx. A equals, let's see here, so that's x to the fifth, 3/5 from 1 to 0. So the area of this thing is 3/5. Well, that worked out nice and clean. We like it when it comes out clean like that. Okay, so we're going to scroll back up here, and now we know the denominators of both of these is 3/5. Okay. Okay, so now up here, I'm not going to worry about the denominators for a bit. I'm just going to write them as a capital A because that's what they are, right? Because I don't, I'm just not going to worry about that. I'll write in 3/5 when it becomes convenient to me. And now we need the x tilde. So the x tilde over here is x. Okay, and now we need the dA, which, I can kind of plug in a dA wherever I want. And so I'm actually going to plug in the dA right here, right? Because I know that I'm going to need it to be in terms of x. So 3x to the fourth d. So 3x to the fourth dx. Okay? Over here at y, I'm going to get the integral of y over 2. And for the dA, I'm actually going to leave it in terms of y, since that one's in terms of y. So y dx. Okay? So now I'm going to work the x bar, and then we'll come back and we'll work the y bar. Okay, noting we're going from 1 to 0 in the x's. So we'll go x bar equals integral from 1 to 0 of 3x to the fifth dx over a. So x bar equals, let's see here, x to the sixth, 3/6, so what's that, 1/2 x to the sixth, is that right? Yeah, I think that's right. Okay, and we're going to go from 1 to 0 over the area, which I decided was 3/5. Okay, so I'm going to plug that a back in. Okay, so the x bar equals 1/2 divided by 3/5. Okay, so the x bar equals, what is that, 5/6? Okay, we'll check to see if that makes any kind of reasonable sense in a second. But all right, so let's go over here, and I've got y bar equals integral. I'm going to pull out that 1/2 because I don't want to deal with it. And I've got the y squared. So let's just leave it as y squared for now over the area. And we'll go y bar equals 1/2 integral. What is y? Y is 3x to the fourth. So 3x to the fourth squared dx divided by the area, which I'm still going to just leave as the area for now. So y bar equals 1/2 let me go ahead and square that. So what's that going to be? 9x to the 8th dx over the area. And so y bar equals 1/2 of, let's see, so 8 goes up to 9, x to the 9th, achi-machi. And then I get, oh, I guess that's it, isn't it? Yeah, cool. Okay, from 1 to 0. Okay, and then this area on the bottom, I'm going to go ahead and put it back in as 3/5. All right, so y bar equals, is that 1/2 divided by 3/5 also? That is really crazy. Is it 5/6? That seems unlikely. I think it's just kind of like an interesting case. It just turns out that it's 5/6 in both directions. That's really odd. Okay, so let's go ahead and see if that makes any sense. Okay, so I'm going to go ahead and erase all this. And then we want to think about where's 5/6, 5/6, and whether or not that makes sense for the centroid of this whole thing. So, you know, I'm not sure if it makes logical sense to me. I'm sure that it's right. I mean, it's not completely absurd, right? So in the x direction, 5/6 might be, so like x equals 5/6, might be about like right in here, right? Okay, so that seems about right. And the y direction, I don't really know. Let's see. So this would be y equals about 1/2. So 5/6 is maybe about, sorry, that's 1.5, right? What is this point right here? Well, if I plug in a 1 for x, for y I get 1? No, I get 3, sorry. 3, right? So this is 1.5. So this is y equals 1.5. This is y equals, I don't know. Let's try 1 is about right here, maybe. It's like y equals 1. So we're going to get, like 5/6 might be like right in here, maybe. Or whatever. Okay, so we got 5/6, 5/6. Okay, if this line right here is y equals 5/6. And it's reasonable, I think. You know, I think I would have thought the y value would have been higher than that, but you know, it's not so far off that we would, you know, trash our work and start all over again. At least not according to my intuition. But so I think we're okay. Anyway, so let's go down here. Oh yes, these are nice because they're easy to grade, but they're not nice for any other reasons. Hey man, what's up? Okay, sorry about that. The mailman came by. Anyway, let's see here. So x is this is 7 millimeters, and r is 4 millimeters. Okay, that's pretty obnoxious. I have to squeeze it in there. Okay, locate the centroid of the cross section y bar, and determine the moment of inertia of the section about the x prime axis. Okay, so the y bar axis, I'm going to make a guess here. I'm just going to kind of throw it out there. My guess is it's on the low end of the middle, right? So I'm going to go ahead and put it, I don't know, let's put it right here. Okay, y equals y bar. This is also called the x prime axis. Okay, and that's of course totally annoying, but you know, it is what it is, right? And anyway, so it has a thing of y equals y bar. So we don't know where it is yet. What we do know is that we've got a number of shapes. There's a number of different ways that you could approach this problem. I think I learned and then I forgot as I taught this course that it can be helpful for me to define the shapes that I want you to use. So for this one, I mean, you could do a lot of negative spaces and things like that. But what I'm going to do is I'm going to split it up into this rectangle, which I'm going to call shape 1. This circle, which is a negative space, I'm going to call that shape 2. And this triangle, which I'm going to call shape 3. Okay. Now, the first thing, before I even begin, I think maybe I want to figure out where my centroids are. And so for the rectangle, let's see, what color can we use for this? Maybe they have another color we can use that's, that will actually show up. Maybe I'll use like a purple. Okay, so for the rectangle, which is 25 by 44, it's going to be at 12.5, right, and 22. But we're not really worried about the the x location, but it's going to be at 12.5. So I'm going to go ahead and put that about right here for the rectangle. Okay, for the circle, it's right in the middle of the circle. And for the triangle, it's 1/3 the way up from the flat edge, right? So if that whole thing is 25, it's going to be 8 1/3. Now this was an annoying thing that I did, which was defining, giving this a 25, not something divisible by 2, not divisible by 3. So it's going to have annoying, numbers going on here. But these are the centroids that we care about. Okay, so for the rectangle, its y hat, or y tilde, is, let's zoom way in, is half of that 25, so it's going to be 12.5 millimeters. For the circle, it's wherever the center of that circle is, so its y tilde is 12 millimeters, okay, because it's at this height right here. And then for this guy right here, its y tilde is 1/3 of the height of that triangle. So, and it's 1/3 of the way from this flat edge. So that's 25 millimeters divided by 3. Okay? So, so now we're going to go ahead and we're going to do our chart here. Okay, where's my chart here? Okay, so we got x. We don't need to do y, so we won't do y. X, and then a, and then x tilde a. And let's just go ahead and do that real quick, because we remember the formula for this. Wait, we don't want x tilde, we want y tilde. Excuse me. Come on, you can do it. Come on. Okay, there you go. Y tilde. Okay, so we remember that the formula for this is that the summation of y tilde a over the summation of the a's, right? So that's for y bar. Okay, so y tilde for shape 1 is, well, let's call shape 1, this will be the shape. Okay, shape 1 is the rectangle, shape 2 is the circle, shape 3 is the triangle. Okay, we need to make sure that our area here is negative, okay, because that's a source of errors, I guess. So, okay, so for the rectangle, we've got 12.5 for the y tilde. Okay, for the area of the rectangle, it's 25 times 44, which I believe is 1100. Okay, and then, and we'll do the next row next. And then, so for the circle, the y tilde is 12. Okay, and then for the area, it's going to be, what, pi r squared, so 16 pi, which I could leave as 16 pi, but I think, for me at least, I prefer, I don't really know what I prefer. 16 times pi, okay, 50.265. I'm going to have to put it in the calculator eventually anyway. And then for the triangle, it's 25 divided by 3, so 25 divided by 3 is 8.3333. And then the area of that triangle is base times height, so 7 times 25, which is 175, divided by 2, right? So that's 87.5. 87.5. Okay, so you can see, like, right off the bat that this rectangle is dominating everything, as makes sense. And what you'll find when you have one particular shape doing that is that the overall y bar is going to be close to the y bar for the rectangle, because it has so much more area. So let's go ahead and we'll do the math there. And so what we're going to do is we're going to multiply this column by that column. So 12.5 times 11,000 is, sorry, I need to get my black color back. So it's going to be 13,750. For the next one, it's going to be this crazy number times 12. And we're going to get negative 603.19, which seems like a big number, but compared to 13,000 or 14,000, it really isn't. And then 25 divided by 3 times 87.5, and we end up with 729.17. Okay, so if we add all these up and we add all these up, so we can get the numerator and the denominator of this particular thing. Okay, so keeping 5 sig figs, as you guys know I like. Well, or really what I'm saying is keep at least 5, because you won't have any rounding errors that way, or at least nothing significant. But the numerator is 13,876, and the denominator is 11,337.2 millimeters squared cubed. And so y bar comes out to 12.202 millimeters. Okay, cool. All right, so that's great. If I wanted to at this point, I could create a y bar. So this would be a row, but this would be global, right? So it wouldn't be for each individual shape, but 12.202, 12.202, 12.202. And in fact, when I grade these, this is exactly how I create it. Just because it makes working in a spreadsheet very simple, because that's kind of what you're doing. You're almost creating, your own personal spreadsheet here. Anyway, so that's cool. Now, I wanted to note two things. Like I suggested, first of all, this shape was the most important one. So we were going to be very near to that y tilde. Y bar was going to be near that y tilde. The other thing is that, we can see that my initial guess that it was going to be below halfway was pretty good. So we're at 12.2. So it's actually above this circle right here, even though I didn't draw it above. And that's our next question, is now the distances between the global centroid and these local centroids, right? So we could call this row the distance, or we could call it y bar minus y tilde. Okay, and we'll take the absolute value of that for the distance, right? So that's what these distances are right here. So each one of these has a distance. And, and luckily these are, basically we're going to take this row, we subtract that row, and we're going to ignore any negative signs, right? Okay, and so those are our distances. And then, why are we doing this? Sorry, I should back that up, right? We're doing this because the IXX bar equals the summation of the IXC plus AD squared, right? So right now what we're trying to get at is AD squared. And we'll talk about that in a second, what that means. But right now we're kind of in a computation mode. We're not really thinking a whole heck of a lot. So AD squared is basically, now I'm going to take this row right here, or this column, excuse me. I'm going to multiply it by this column squared. Okay, and so if we do that, we get something that looks like, like these particular numbers. And, I should note that, it's interesting because now it seems like the triangle is dominating the bending. And to an extent, that is definitely true. It is dominating the bending due to how far its centroid is away from the global centroid. And I'll talk about that in a second, because there's a reason we have both of these quantities. So let's go ahead and calculate the IXC, okay? And so for a rectangle, it's 1/12 the base, in this case 44, times the height, 25, cubed. Okay, so it tends to make it a pretty big number. It isn't always, of course. It really depends on units. Okay, but I'm getting a number like 57292. Okay, and that's in millimeters to the fourth. Okay, that's a pretty big number. Okay, for a circle, it equals, let's zoom in here. For the circle, it's, and these are things that you look up on the chart, right? So it's going to be pi times the radius, which is 4 to the fourth, divided by 4. And that's just a formula you look up, right? So pi r to the fourth, to the third. Okay, and we get 201.06. Okay, and then the last one is a triangle. And triangles are 1/36. The base, in this case, is 7 times the height, which is 25 cubed. And so we're going to get 3038.2. Okay. Now to solve this whole thing, all we're going to do is we're going to sum all the IXCs and all the AD squareds. So we'll say IXX prime equals basically the sum of all of this. So what I'm going to do is I'm going to add up this column, I'm going to add up that column, and then I'm going to add them together. But I also need to remember that the circle is negative, so we're going to subtract those. Okay, so just be careful with that. Okay, so now I've just summed those two rows, and I got this value and I got this value. And then I'm going to add them together. Okay, and I get 61,534, and that's millimeters to the fourth. Okay, and of course, you know, you guys know me, I don't like all these sig figs. So the Y bar is going to be 12.2 millimeters, and the IXX or IX prime is going to be 6.15 times 10 to the fourth. Okay, 3 sig figs. Okay, one thing I want to talk about here real quick before we move on is that we've got these two quantities. We've got this one and this one. This one is how hard it is to bend the shape around its own axis, axis of symmetry, neutral axis, centroid, whatever it is you want to call it. This thing is basically the correction. So this is basically how much harder it is to bend it around some other axis. Okay, so in other words, you know, and which other axis? Well, the axis that is d distance away, right? So in this case, so for example, most of the difficulty of bending around this xx axis, which implies that we're bending it kind of like this, okay, if you can imagine what that means, is most of the difficulty here is the fact that the rectangle is just really, really, really stiff. That is the vast majority of this, okay? Other than that, you know, the circle doesn't matter very much, okay, in either case. And this is one of the reasons why you can hollow things out and they're still hard to bend, okay? One is because it's local, you know, it's not that hard to bend this little shape in the middle here on its own by comparison to the big shape. And then the other thing is because it's close to the centroid, because its centroid is close to the centroid, it doesn't matter all that much. Okay? If we had decided instead to hollow out, say, this corner or something, then it would have mattered a lot more. But we didn't hollow out that corner. Okay? So that's why it, you know, it doesn't really have a very big effect. Okay? As far as you know, how much harder it is to bend it around some other axis, you notice that the triangle right here, it had the largest value, and that was simply because its centroid was the farthest away, okay, from the global centroid. It still wasn't terribly important because this triangle is 7 by 25, whereas this main thing is 44 by 25. So the triangle is just not really that important, okay? And in this case, everything basically is just dominated by the sheer size of that rectangle. Okay, so that's just kind of a thought process of what these numbers are. I always find these numbers frustrating because I get an answer like some number of millimeters to the fourth, and I have no way to kind of get a feeling for whether or not that's a reasonable number. This one I can get a feeling for a reasonable number. I just don't know how many. I can't look at this and be like, oh, this is going to be a certain number of millimeters to the fourth. If ever you're stuck with one of these problems, and you do want to know whether or not your final answer is remotely reasonable, one thing you can do is you can stare at it and you can say, what if this was an entire rectangle? Right? This rectangle, that big rectangle would be harder to bend than the smaller one. I mean, than the smaller shape, right? So I might say, okay, well, let's just calculate the moment of inertia for that really big one. So 1/12, the base of that thing would be 51. the height would be 25. And you could do this little math problem right here. And I could say, okay, well, 1 divided by 12 times 51 times 25. And you get a number like, 25 cubed. Why is my thing not working? It's not writing, sorry. Cubed. And you get a number like 66,406, right? Okay, and that's millimeters to the fourth. Okay, this would be an upper bound. Okay, if I got a number bigger than 66,000, I would be thinking that I'd done it wrong, right? And I'm at 61,000. I've got a lower bound, and it's not necessarily a lower bound because that circle has been cut out, but my lower bound could be that shape right there, so this is 57. So I would expect my answer to be somewhere between 66,000 and 57,000, and I got 61,000, which makes me feel pretty good. Okay, so it's just an idea. All right, so this last one, solve for the forces, and now this is always annoying, right? Because we have to try to figure out which ones it is they want. In GHHE, so GH is right here. I say they, I created this problem. HE, here's HE, and DE. Okay, so then when they're nice and clean like that, that pretty much tells us that we're going to want to do this by sections. You can do it by joints. I am not going to do it by joints because, I have a life to live, and I don't feel like doing that, okay? So what we're going to do is we're going to cut it there, and what that means is I got to get this force, I got to get whatever's going on with this roller, and that's it. And I'm going to do the right-hand side. I could have cut it and done the left-hand side, but if I'd done the left-hand side, I have to deal with both of those forces in my free body, and I'd rather have fewer forces, so we're going to do that. Now, the problem is I can't, so if I draw that, let me go ahead and draw that real quick. So if I draw this, I think you'll notice that, so I'm just drawing the free body diagram of the right-hand side of this thing. I guess I could use some, this is 40 feet and this is 30 feet, right? So that's pretty helpful. But what you'll notice we've got 4 unknowns here. Okay, and I've only got 3 equations. So what I need to get rid of one of these unknowns, and F is the one that I'm going to have to get rid of. I need to figure out what F is before I move on. So I think typically most of my students will solve this by immediately solving for the reactions. And I get that, and that's totally fine. However, if you're stuck for time and things, you might say, you know what, I only need the reaction at F. I don't really need anything else. I don't need what's going on at A. So what we can do is I can go back up to this big drawing up here, and I can say, okay, well, I've got an F right here. Okay, I'm not even worried about what's going on at A. I'm just going to sum moments around at A. Okay, because that's going to give me F. Right? I know that there's some forces at A, but I don't care what they are. Okay, because I don't need them to solve this problem. So let's do the sum of the moments at A equals 0. Okay, and I've got this P. Let's see, so P, well, I don't want to write P. I'm going to go ahead and write 6. So 6 kips times 40 feet. Okay, and we remember this is positive, so this one's going to cause kind of a negative rotation. Okay, minus the Q, which is 7 kips, and it's got a distance of 80 feet. Okay. Minus R, which is 2 kips, times we got now 120 feet. And then we're going to add F, and it's now got an extra 40, so it's 160 feet equals 0. Okay? So, and that's the nice thing about having a roller also on the right-hand side, right? So I'm going to go ahead and say, just solve this, and I get F equal. I'm getting 6.5 kips. Okay? I hope that's correct. All right, I mean, I'm actually working this whole key raw. Normally I work the key out beforehand, but the problem, of course, the key beforehand's got variables on it, so it's a little bit more annoying. Anyway, so what we're going to do now is, we're going to insert that 6.5 kilonewtons, and then my 3 equations and I only have 3 unknowns, so that's like, So now we can work this out. Okay, so let's go ahead and do it. Okay, so you know, I think you guys know that, well, I'm going to go ahead and put some letters on here, F, E, and G. Okay, so I think you guys know that I like to think about my equations before I solve them. And we notice that in the x direction, I've got 3 unknowns, so I'm not going to do that x equation first. In the y direction, looks like I've got 1 unknown, which is EH. So that's pretty cool. I could do y first. And I don't think I'm going to do y first, but there's nothing wrong with doing y first. It doesn't really matter because it's going to come out, like I'm essentially doing it first because I'm going to do it without getting any other information that's going to help it. But then for the moment equation, depending on where I do the moment, so if I do it at E, for example, there's 1 unknown, GH. If I do it at G, there's 2 unknowns. So if I do it at E, so if I do the moment at E, then there's 1 unknown. Okay, so the logical thing here is to do either the sum of the forces in a Y or the sum of the moments first. Okay, so let's start with, I'll do Y first, never mind. Okay, we'll do Y first. Okay, so I've got negative 2 kips. I've got plus 6.5 kips. And I've got plus EH. Okay, and then I've got, well, you know, the sine of some angle, right? The sine of theta equals 0. So we're going to call this angle here theta. Okay, now I'm going to note real quick that for a lot of you guys, so this angle is also theta. So for a lot of you guys, we'll go ahead and solve for what that angle theta is. I am not, because it's going to be easier to, what is the sine of theta? Well, the sine of theta is the opposite over the hypotenuse, right? So it's 3/5. Okay, so I'm going to do that. So negative 2 kips plus 6.5 kips plus EH times 3/5 instead of the sine of theta equals 0. Okay, so we'll go ahead and solve this, and I'm going to get EH equals whatever it is. So I get EH is 7.5 kips, which is a nice clean number. Cleaner than I was expecting it to be. But, you know, we're very happy with that. Okay, so now we'll do the moments, and I'll do the sum of the moments around, and like I just said it earlier, I'm going to do it around E, because, you know, that gives me this really nice advantage that DE and EH both go right through the middle of it, as does this 2. Okay, so let's go ahead and see what we can get. So I've got GH, okay, times its moment arm. So its moment arm is right here, so that's 30 feet. Okay, and that's causing a rotation this way, which is the same as our positive. Okay, and then we've got the 6.5, which is kips, which is causing a rotation in the same direction. Okay, and its moment arm is 40. Okay, so GH comes out to, you know, we've been foiled by being given a bad number here. Anyway, so now that we've done Z and we've done Y, there's actually only 1 unknown in X now, right? So we can do the sum of the forces in the X direction equals 0. And, oh wait, sorry, GH is negative. So that means that I've got negative GH minus DE minus HE times the cosine of that angle equals 0, or EH, excuse me, EH, right? Okay, so let's see here. So we've got negative 8.6667 kips minus DE, which is what we're looking for, minus EH, which is 7.5 kips. And then for the cosine of this angle, remember I'm going to do the adjacent over the hypotenuse, so that's 4/5 equals 0. Okay, so if we solve this, we get 2.6667 kips. Okay, so let's see here. So if I go down here and I'm going to put these things in here, I want to note that I assumed that all of these were in tension. So wherever I got a positive sign is in the case of HE or EH, this should be in tension. In DE was also positive, so 2.67. Remember, we're doing 3 sig figs. We're going to call that tension. However, GH was 8.67 kips, and it got a negative sign, so we're going to make that compression. Okay, so that's how you do it. Anyway, so I guess I hope this was helpful, and I hope you guys are taking care of yourselves and that all is well. I think there might be an error in my written key, not in the equations boxed in red, but in the like kind of like when I started doing it with the variables. I can't really tell for sure. Anyway, at least for this problem. But anyway, I hope you all are well, and I hope this was helpful. All right, goodbye. Damn it.